everyone decided on, and I'm using orange as a color right now. I guess it's yellow-orange. And hopefully the icons are somewhat appropriate. But the topic is that if we'll leave it as an open forum. I'll start off with a couple questions. Do people want Amane to continue? Because there's a couple other concepts that he wanted to go through, and we could sort of just talk in general. But otherwise, we would segue, because there's a lot of thought about how do we better maximize the data that we have, how do we deal with signal and noise. And it's great to have an algorithm, but an algorithm is not a package. And then from a package, there's a big step to an end user saying, okay, now I can apply this to my data. So what we want to do overall is try to lower the barriers of access. And we're doing it on the backs of a lot of the academic programmers that don't have a lot of funding, that don't have a lot of resources. So there's sort of this conundrum where, like, we want a physical, nice GUI interface product, something that I can just press one button. But do you want to support the people who are not only applying that in a reasonable way, doing validation? And programmers are expensive. They rather go to Google and Facebook. They rather not stay in an academic lab. Okay, so these are topics we want to go on to. But since we cut Amade a little bit short, perhaps you can touch upon a couple of other things that you were going to talk about, and then we'll segue more into that discussion. So, local resolution, or the local refinement?
What are the topics you left out?
Yeah, the last I wanted to talk about was the. So it's important for classification to have fine angular increments. So you refine the angular assignment of each of your particles as precisely as possible. It's important for classification and for resolution. But then when you have a very flexible molecule or very large molecule, you might actually need to refine those angular assignments even further locally. So you want to actually basically mask a specific portion of your protein, which is a little bit blurred away by its flexibility, for example, and then basically refine further your angular orientations around this particular portion. Now, there are some issues with doing that. One is the smaller the size of the particle, the harder it is to align. And so if you want to, and so basically you're limited there, basically by something that's fairly fundamental to cryo-EM. And so usually masking an area and refining that particular area, well, it's actually been in a way measured by Hongwei Wang at Tsinghua University lately, where he managed to actually align properly a domain of a protein that was in the order of 40 kilodalton. So
how many?
40 kilodalton. So you can, in theory, with fantastic sample quality, beautiful contrast, go all the way down to basically refining the angular orientations on a 40 kilodalton domain of your protein or complex. Let's say more generally, you will be limited to somewhere around 100 kilodalton. That's usually, like, beyond that, it starts to kind of not work so well. I think for the renin receptor, the best, it also depends on what is flexible in your molecule, and like how basically which domains are moving with respect to other domains. So you have to play around with that. But basically, maybe you want to sample different size masks that include bigger and bigger or smaller and smaller regions, and see which one gives you the best result. So for renin receptor, when we did that, or when I should say, when Oliver Clark played with that, the sweet spot was 300 kilodalton. At 300 kilodalton, which is fairly small compared to a 2 megadalton machine, that's where he got the best maps. And actually, I said best maps because when you do those things, you have very tight masks around your particle. The resolution you measure might be influenced by the mask you use, and so it's very easy for the resolution measure, the Fourier shell correlation that others have been talking about, to give you a result that's not exactly what is real. So the only way to look at whether you're improving things or not at this point is really looking at your map and saying, okay, is this sidechain better defined now than it was before? Can I see a sidechain here when I couldn't before? That's your measure.
Have you ever done the analysis where you used the classification to help you map the trajectory of a domain? So usually you do morphs between different states, but have you done fine classification and say, like, okay, this is the actual dynamic pathway based upon the kinetics of the data that I have?
So that's a very pointed question. So there are new algorithms based on. So basically, when you do, that's actually a very important point, which is when you classify your data. So ReLion has been the go-to algorithm for many years, where you say, okay, I'm gonna classify my data. Let's give it 4 classes, so k equals 4, and then my particles are gonna basically randomly be assigned to those 4 classes, and you iterate through that many times and update your references, and things are gonna diverge, and your different references are gonna diverge and give you 4 solutions, with your particles being basically distributed between those 4 solutions. Those 4 solutions may have nothing to do with reality. And it's important to remember that. Those 4 solutions might be 4 averages of many solutions that just ended up to be put together in a class. And so it might be better to actually get larger number of classes for that not to happen. But then if you have too many of those classes, you end up with also with fake classes where you think they are different, but actually it's 2 slightly different alignments of the same population of particles. So basically there's no good answer to doing this in a discrete way. Also because, let's say you say 8 classes, or some people have gone all the way to 50 classes. I have 50 classes. Then how do you figure out, let's say, if your molecule is actually oscillating between different states, how do you figure out the path between those 50 classes? You actually don't know. So there are potential ways to do that. So, and my math background is not kind of good enough to tell you much about it. So you can do some analysis to kind of cluster the volumes, the most similar volumes together, and the most dissimilar, putting them elsewhere, and trying to organize some kind of energy landscape. But let's say it's fairly dangerous to do that at this level. And if you're just by eye opening your volumes in camera and trying to figure out like which one is number 1, number 2, number 3, and trying to make a movie out of it, it's most likely going to be wrong. So some people have been designing programs, and some people, I'm actually pointing to Abba Sumzar's group at University of Wisconsin-Madison, using basically some geometric machine learning algorithms where they are basically, instead of doing 50 maps, 50 models, and 50 references and trying to sort them out, saying, okay, I actually have 1 million particles, and so my 1 million particles don't need to be the same. They are most likely all different to some extent. And so, and you can basically calculate how different they are from each other. So you can say, okay, I'm comparing 2 particles. What is random between them? So there's no particular correlation. So you can take each pixel and say which pixels are changing randomly between those 2 particles, and which pixels or set of particles, and which pixels are changing in a coordinated fashion. So when this one is getting more dark, this other one is getting more white, and so there's some coordination there. And so you can sort of reduce, do something that they call a dimensionality reduction, where you kind of forget about everything that's random and only look at sort of the correlations between pixels that are meaningful, and you get some kind of what we call reaction coordinates, or some modes of motions in some n-dimensional space. And usually it's going to be a 2 or 3 dimensional space, because you can't really get much signal out after that. And so you're going to get some kind of energy landscape based on those correlated motions, those modes. And so that way you're really looking at individual particles and how they cluster with each other. And because now you're looking at not 50 but 1 million particles, you can actually find those basically the geometry of those energy landscapes in a way. And so you can travel, let's say it's going to make some hypersurface, and you can travel along that hypersurface, which is basically your energy landscape. Because if particles are clustering around a certain region of that space, it means this is a low energy state, and if they are in places that are more sparse, it means it's a higher energy state. And so in that case, and so you can relate that with the Boltzmann function to basically an energy landscape, a free energy. And so now when you travel from one place on that hypersurface to another, now it's becoming much more of a real movie going from one state to another. And you actually have data between, like at every frame of that movie, because you're not morphing two sets of particles, you're actually kind of reconstructing 3D volumes along that path. Does that make sense, or is it a little... And maybe you have a clearer way of describing it. That's very possible.
Well, I wanted to make a plug for two of my friends. So Jacob Anden and my colleague Hema Tagari have been working on this problem too.
Yep.
And so remember, the problem with classification is the model is saying we have k different discrete volumes or k different discrete underlying images, and we're trying to estimate the best estimates of those. And so it's clearly wrong, because if we have continuous variation, then having these individual classes is wrong. And the other thing is, when Reliant assigns a particle to a class, it's just telling you which class gave the highest gamma value, which had the highest probability, but that it's a fuzzy assignment that he's then making hard because he's only reporting the best assignment. My mathematician colleagues there's a wonderful theorem that they've discovered, which is, you know the Fourier slice theorem that lets us do 3D reconstruction. Turns out there's a Fourier slice theorem for covariances. So that means that you see how in in particle images, maybe this pixel gets dark while that pixel gets bright, because you have a motion like this in your particle. That can get mapped unambiguously onto 3D. So software is coming that will give you these 3D principal components of variation. So it's just like what Amadei said. So when you have a large data set in the now or in the future, it should be relatively straightforward to say, okay, here is my average model, and one of the ways in which things seem to vary in my data set is that this part gets dark and this part gets bright. No doubt something's moving in that way, and then you have another principal component that says, here this blob disappears or reappears. Aha, I have heterogeneous, binding subunits and so on. Yeah, so this is very exciting, and the whole idea of getting the energy landscape is coming. We just need really big data sets.
Yeah.
So I'm going to switch topics a little bit. So something that Amade was talking about was the resolution you get depending on how well you can estimate your defocus and other things. Something that Fred has been working on is looking at membrane proteins embedded in liposomes. So then in your modeling and you're treating that, let's say like a potassium channel or something like that, how do you handle the large curvatures of that depending on how large you can make a liposome, and how do you deal with that also given that we want to put it in a membrane environment, but that is also noise, or it could be signal, depending on what you're going after.
So, so first the second issue, which is so we have a liposome, it's like a soap bubble, and we have our protein sitting in it, and there's a very strong signal from the membrane. So this is really a subtraction issue. We have to subtract enough of the membrane's contribution to the image so it does not screw up the orientation determination. Now it turns out that that's not too hard. So we make a model of what a liposome looks like, operate on it with a CTF, we fit it to each liposome in the image, and we do a subtraction, and then we reconstruct the subtracted particles. At the end, we can go back to the unsubtracted particles, do the using the orientations determined before, and get the particle and the membrane all back together. Now, the problem is it's impossible to make liposomes of all the same size, so there are going to be various curvatures, and so far we're working at low enough resolution, still stuck at sub-nanometer, that we don't know if there's a problem. It doesn't seem to be a problem with curvatures, because if we sort the particles, we get the same result. But no doubt at high resolution, we will see that our ion channel is going to have its helices in a little bit different place in high curvature membranes than low.
So something that Fred had done before was doing local resolution estimations from cryo maps. How hard was it for you to find someone to work on that project and program package that is basically ResMap?
So I've been really lucky because it's pretty easy to talk to other people at Yale, and so I've gotten a couple of math people excited about cryo-EM, and one of them is Hemant Tigari. So he's the one he and his graduate student got excited about that. So I think the quick answer is collaborate with somebody.
So Amine, when you're looking for people to help you in your lab for cryo-EM, in what fields are you looking for? Because you're a cryo-EM expert. Maybe you want to train them, maybe you don't want some training, but what other fields are you trying to pull expertise from in your candidates?
So first, it's very difficult to hire people that have cryo-EM experience, so I don't even try. But there is a very, very wide, large pool of crystallographers who want to do cryo-EM. So if you tap into that pool, you can find a lot of people that are willing to learn the technique, and they already know structural biology well enough that, let's say, the technical details of cryo-EM are quickly learned. One thing that I'm looking more specifically in my group is more people who have molecular dynamics experience, or expertise, I should say, because we are moving more and more towards understanding, let's say, complex motions in proteins and how they affect function and how you can use that information to design drugs. And so when we are playing with machines that have hundreds of thousands of atoms, just looking at it is not necessarily enough. And so that's a kind of additional expertise that we might need even to interpret manifold embedding, all these new algorithms that deal with dynamics.
Okay, here's a general question for both of you. So AI is being brought to bear on cryo-EM problems. I suppose particle picking is an easy topic to start with because you can validate that. Right now, people are thinking of an algorithm to employ, and then they implement that. With AI, then you won't know the algorithm because it's generating, and you might, it's actually a box goes into another box to come out of that. So how's your feeling, and what fields do you think that AI is appropriately being used for cryo-EM?
So cryo-EM, one, we have an internal reference which tells us whether the result is correct or not, which is that we know how an alpha helix is formed and how side chains are supposed to be arranged in that alpha helix, for example. And so whenever it's going to give us a result, whichever way it got there, we will be able to tell that's a protein or that is not.
Mm-hmm.
So in a way, hopefully, we won't have issues of knowing whether this was the truth or some fake, some deep fake. But who knows? Maybe we'll get to the point where it's going to do a deep fake alpha helix with perfect side chains, and and we'll be in trouble. Hopefully not.
Yeah, I agree absolutely. I mean, the fantasy is to get the whole movie out of the AI network, and because I don't see a way to do it by classical statistics.
I will before I forget, plug back into this issue of classification with X number of classes versus other algorithms. In particular, to kind of make people aware of, like, it's important to understand where, when you have a classification like Reliant or CryoSpark or system, where you have X number of classes, it's very important to understand where the classification comes from. Meaning, you have a bunch of parameters you can play with, such as, let's say, the accuracy of alignments, like how fine you're sampling, the resolution at which you start, the resolution at which you finish, or you limit yourself, how fast you go from one to the other, like the gradual descent toward higher resolutions. So all these things are extremely important in what result you get at the end. And so in a way it tells you how wrong, or how, let's say, incomplete, I would not say wrong, because it gives a lot of beautiful structures that are mostly correct, but how biased that is, because let's say you do two classifications, one where you start at 60 angstrom resolution with your reference, another one where you start with 30 angstrom. You didn't really know why you chose one or the other. The result at the end, the classes you get, are completely different. Like, you have a completely different distribution of end results. And that obviously has nothing to do with the particles themselves. They didn't change. So it's only the way they got grouped based on the signal that you're giving them. And so the alignment, the coarseness of your alignment is important. Like, at an extreme, if you do such a coarse alignment, a very, very coarse alignment, you will classify it based on view. So class 1 will have view 1, class 2 will have view 2, class 3 will have view 3. And I've seen that very frequently, especially when you have preferred orientation on your with your sample. Like, oh, this one is crap and this one is a good one. And you get rid of this one, but then actually it had 50% of your data. It was just a different view. And it looked bad on one side, but if you turn it around, it looks actually pretty good. So always be careful about that. That, like, views get very easily clustered into different classes because there are different slices in Fourier space, and they don't talk to the other slices. Only basically in that central slice, in that central line. So that's a very, very important thing to think about. But then also some features that are at low resolution, other features at high resolution. So a large domain movement, you might want to restrict your resolution of your classification to very low resolutions so that you catch the very large movement of a certain domain. And that will give you a different result than if you go for very high resolutions, and now it's going to get all your particles that look good to go to one class because they look good. They have high resolution features. And that's actually a way to clean up data. Yeah, so that's one aspect of Reliant specifically, which is your classification is really very much driven by information content. And so if you look at your Fourier transform, let's say this is the Fourier transform, and I put the dirty side because it's dirty, there's lots of noise. When you start at low resolution is a single little point in the center here. And high resolution is basically the rim of the plate. So you see the surface area of low resolution is like that, let's say 20 angstrom and less, is like the size of my, the tip of my finger. 4 angstrom resolution and better is all of this. And so if you don't restrict resolution, and that's extremely important in 2D, it's very important in 3D as well. If you don't restrict the resolution limit, it will basically, all your particles will try to cluster so that they maximize their agreement at high resolution. So if you have a kind of a broad domain movement, that's a low resolution feature, it's going to ignore that completely. So you'll see one class, sharp core, blurry sides, because that's what you basically told it to do. So that's a case where you want to limit resolution, let's say to 20 angstrom, so that it doesn't focus on that portion of the Fourier transform, it focuses on here, those broad motions. And that's something that very few people in the cryo-EM world think about and look into, but it's extremely important.
We're going to pause here, and we're going to come back. We're going to take a photo. And how long do you have to come back? Because what we can do is we can delay the start of the practical, because it's very rare to have people here. And I haven't heard much engagement from the students, and that's more what we want. So if need be, after the photo, if they can stay around for a little bit, then you can interact in a more informal manner, maybe because the microphone is here, so you feel a little bit, you don't want to watch what you said, but you do that. So let's
Can I add one last piece of information, just because it's related to that, and then you're gonna forget
then we can get a
about
photo.
It's like this is something that's first described in Rosenthal and Anderson in 2003. A very famous paper that everybody should read. The information you need to align particles is between around 100 angstrom and around 30 angstrom. That's what you need to get accurate alignment of your particles. That's at the time of that paper. There was no particle less than 500 kilodalton. So that's, if you have a smaller particle, it's actually not it's not exactly the same. You need maybe 10 angstrom resolution. But you have that window of resolution that you need to align your particles. So if you play with these tricks about limiting resolution to get your broad movements, but remove too much resolution, too much high resolution that you can't align your particle, then you will not get the answer that you hope for. So always be careful. There's a trade-off between resolution you use and what you need to actually align your little particles. I'll stop there.
Okay, so let's go for a photo. We're going to brave outside. We're going to take one photo with the students only, and then one photo with everyone.
Aladi, are you going to be here?
I'll be here for a little bit. Then I need to cross to the side, but I'll be here for a little bit.
Okay, I have a ribosome project going on, like we're actually collecting data. And so these are hyper-modified ribosomes. So they have all these like modifications and so on. So we have these mutants which do not input all those modifications. So I'm comparing the wild-type ADS with the hyper-modified ADS. Right? Now the problem with the hyper-modification is not all or none. So we know there are like 50, 60 points of modification. So some of the modifications we know from like biochemistry work that are 100% gone, some are like 50% gone, some are 30%, or some are not gone at all. Right? So I want to get like your ideas about how to do this. I mean, I already asked them to just collect as many as possible because I think that it's less.
idea that if this happens very often is because the resolution was not, there was, you did not limit the resolution enough. If you limit the resolution, basically the Fourier planes are.
So the
getting
plan
closer
here
to-
is we'll give another 15 minutes to decompress, also chat with Amade and Fred.
That would be the
And then
first
in
thing.
15 minutes,
To
Misha
align
and
the
Micah
particles
will
first.
come here, and we're going to
then do a
segue.
local
If you want to stay
classification
for the
exactly
practical,
what-
you're more than
global
welcome.
classification.
We're going to segue to the
Very
NCCAT
local,
area,
they
and we're going to
find
begin
something.
the tutorial
Less
So
using
145, right?
145. So if you want to use the bathroom, you want to talk more with Fred, informal, we'll turn off the. I'm muting the.